We are here to teach you on how to solve initial value problems with the use of Laplace transforms. So next slide please. Okay, so the initial value problem is y double prime plus 4y prime is equal to cosine t minus 3 plus 4t. And then our y quantity 3 is equal to 0 and our y prime quantity 3 is equal to 7. So first thing that we will need to do is to take care of the fact that the initial conditions are not at t is equal to 0. The only way that we can take the Laplace transform of the derivatives is to have the initial conditions at t is equal to 0. This means that we will need to formulate the IVP in such a way that the initial conditions are at t is equal to 0. So this is actually fairly simple to do. However, we will need to change the variable to make it work. So we are going to define n is equal to t minus 3 or t is equal to n plus 3. So let's start with the original differential equation. So y prime quantity t plus 4, again, y double prime quantity t plus 4y prime quantity t is equal to cosine t minus 3 plus 40. So notice that we put in the t part on the derivatives to make sure that we get things correct here. So next, we will substitute in for t. So y double prime quantity n plus 3 plus 4y prime quantity n plus 3 is equal to cosine n plus 4 quantity n plus 3.
Now, to simplify life a little, let's define u of n is equal to y quantity n plus 3. Then, by the chain rule, we get the following for the first derivative. And it is u prime of n is equal to du over dn is equal to dy over dt times dt over dn is equal to y prime quantity n plus 3. Now, by a similar argument, we get the following for the second derivative. U double prime of n is equal to y double prime quantity n plus 3. The initial conditions for u of n are u of 0 is equal to y quantity 0 plus 3 is equal to y quantity 3 is equal to 0 and u prime of 0 is equal to y prime quantity 0 plus 3 is equal to y prime quantity 3 is equal to 7. Now, the initial value problem under this variable is then u double prime plus 4u prime is equal to cosine quantity n plus 4n plus 12. Now, with given of u quantity 0 is equal to 0 and u prime quantity 0 is equal to 7.
This is an initial value problem that we can use Laplace transforms on, provided we replace all the t's in our table with n's. So, taking the Laplace transform of this new differential equation and plugging in the new initial conditions gives s squared u quantity s minus su quantity 0 minus u prime quantity 0 plus 4 quantity su quantity s minus u quantity 0 equals s over s squared plus 1 plus 4 over s squared plus 12 over s. So, quantity s squared plus 4s u quantity s minus 7 equals s over s squared plus 1 plus 4 plus 12s over s squared. Solving for u quantity s gives quantity s squared plus 4s u quantity s equals s over s squared plus 1 plus 4 plus 12s plus 7s squared over s squared. So, u quantity s equals to 1 over quantity s plus 4 times quantity s squared plus 1 plus 4 plus 12s plus 7s squared over s cubed quantity s plus 4. So, note that unlike the previous examples, we did not completely combine all the terms this time. In all the previous examples, we did this because the denominator of one of the terms was the common denominator for all the terms. Therefore, upon combining, all we did was make the numerator a little messier and reduce the number of partial fractions required down from 2 to 1. Note that all the terms in this transform that had only powers of ss in the denominator were combined for exactly this reason.
And this transform, however, if we combine both of the remaining terms in the single term, we would be left with a fairly involved partial fraction problem. Therefore, in this case, it would probably be easier to just do partial fractions twice. We've done several partial fraction problems in this section and many partial fraction problems in the previous couple of sections, so we're going to leave the details of the partial fractioning to you to check. Partial fractioning each of the terms in our transform give us the following. 1 over the quantity of s plus 4 times the quantity of s squared plus 1 is equals to 1 over 17 over s plus 4 plus 1 over 17 times the quantity of negative s plus 4 over the quantity of s squared plus 1. So 4 plus 12s plus 7s squared over s cubed times the quantity of s plus 4 is equals to 1 over s cubed plus 11 over 4 over s squared plus 17 over 16 over s minus 17 over 16 over s plus 4. Plugging this into our transform and combining like terms give us u quantity of s is equals to 1 over s cubed plus 11 over 4 over s squared plus 17 over 16 over s minus 273 over 272 over s plus 4 plus 1 over 17 times the quantity of negative s plus 4 over the quantity of s squared plus 1 is equals to 1 times 2 factorial over 2 factorial over s cubed plus 11 over 4 over s squared plus 17 over 16 over s minus 273 over 272 over s plus 4 plus 1 over 17 times the quantity of s negative s over the quantity of s squared plus 1 plus 4 over the quantity of s squared plus 1.
Now taking the inverse transform will give the solution to our new initial value problem. Don't forget to use ns instead of ts. So u quantity n is equal to 1 over 2 n squared plus 11 over 4n plus 17 over 16 minus 273 over 272 e raised to negative 4n plus 1 over 17 the quantity of 4 sine quantity of n minus cos quantity n. This is not the solution that we are after, of course. We are after y quantity t. However, we can get this by noticing that y quantity t is equal to y quantity n plus 3 is equal to y quantity n is equal to u quantity t minus 3. So the solution to the original initial value problem is y quantity t is equal to 1 over 2 the quantity of t minus 3 squared plus 11 over 4 the quantity of t minus 3 plus 17 over 16 minus 273 over 272 e raised to negative 4 the quantity of t minus 3 plus 1 over 17 the quantity of sine the quantity of t minus 3 minus cos quantity t minus 3. Y quantity t is equal to 1 over 2 t squared minus 1 over 4t minus 43 over 16 minus 273 over 272e raised to negative 4 the quantity of t minus 3 plus 1 over 17 the quantity of 4 sine the quantity t minus 3 minus cos t the quantity of t minus 3. That's all. Thank you.